Hello once more. We're about starting the lecture. So just hold on for me to share the screen. Just hold on a bit so I can put it on presentation mode. Okay, so this is our week 2 lecture. Trying to admit more of your colleagues in here. Okay. So we're looking at nature and composition of petroleum and natural gas. Nature and composition of petroleum and natural gas. Petroleum and natural gas constitute another form of fossil material. If you remember in the last lecture, we were talking of fossil material, talking of coal, petroleum, and natural gas. So we're going to look at the composition of natural gas now. So I want to repeat what I said because I got distracted. I'm still admitting your colleagues. That's a great distraction for me. So petroleum and natural gas, they constitute particular form of fossil materials that have been found widespread, and it's a major source of energy and raw materials for chemical industry. So just introducing this topic. So this topic is devoted to the treatment of the nature treatment of the nature and composition of these fossil materials. I mean, petroleum and natural gas, the processing of petroleum for the production of various types of fuel. That's what we're going to see in this lecture today. The petroleum refinery is concerned principally with refining fuel using simple atmospheric distillation and some other refinery processes which we're going to see here. And fuel is primarily refined for the purpose of producing petroleum is primarily refined for the purpose of producing fuel, gaseous fuel, liquid fuel, and even solid fuels. So when we're done with this lecture today, you should be able to understand the chemical composition of petroleum and natural gas. You should be able to know the various fractions that are obtained by atmospheric distillation of petroleum. And you should be able to know the applications, the field applications of these different fractions. See, bear with me. I have to be going back to admit people. Okay. All right. Okay. So let's look at nature and composition of petroleum. You know that petroleum otherwise is called crude oil. Petroleum otherwise is called crude oil. It's a naturally occurring, free-flowing liquid, always found in association with natural gas. In the oil well, where you have petroleum in a liquid form, you will also have natural gas associated with the petroleum there. So crude oil varies in composition. Essentially contains three main hydrocarbon groups. We have the paraffins, otherwise called the alkanes. We have the naphthenes. These are the cycloalkanes. And then we have the aromatic, also the aromatics composed largely of benzene, and its derivatives. So crude oil can also therefore be described according to which particular type of hydrocarbon group is more predominant in the mixture. So, because the crude oil is actually a mixture of different groups, as I've mentioned before, the alkanes, the cycloalkanes, and the aromatics, which compose mainly of the benzenes. So depending on which of these is predominant, then you describe the crude oil according to that particular hydrocarbon that is much more in that petroleum. In addition to the three main groups of hydrocarbons that I'm just talking about, we also have other components and small quantity like sulfur, organic sulfur. We have nitrogen and oxygen compounds also. They're also present in the crude oil. Okay, so separation of crude oils into gases, liquid and solid, is achieved by a simple atmospheric distillation. During this distillation, the liquid fraction of crude oil has wide boiling range. So in most cases, so the gasoline composition of the crude oil is highly naphthenic. So now you have to break the crude oil into different fractions. Fractions based on boiling ranges. Different temperatures, different liquids that boil within a particular range of temperature are clashed together and called fractions. So, and then naphthenes and aromatic contents of a particular straight-run gasoline varies as the boiling range increases. What I mean here, and what I call straight-run gasoline, is the gasoline that is isolated mainly by distillation, by this atmospheric distillation. Along the line in this same course, you will see different other types of gasoline that are not directly from the fractional distillation, that are also derived from other products of fractional distillation that are further distilled to still get another kind of gasoline. So, but the one that you obtain directly from atmospheric distillation is called straight run gasoline. So this fraction is more commonly used as naphtha, especially in the petrochemical industry. So the distillation endpoint of this fraction can vary from about 160 to 190 degrees centigrade. I'm talking of the straight run gasoline fraction. Means I'll show you several other fractions that we have there that boil at different boiling ranges. So, but what I'm talking of now is the straight run gasoline, that particular fraction. Okay, so now let's look at nature and composition of natural gas. Natural gas applies to all varieties of gas. It's a mixture of gases or obtained from underground strata in which the paraffinic hydrocarbons predominate. You have more of the paraffinic hydrocarbon in natural gas. And natural gas usually occur in three different types of reservoirs. One is the dry gas reservoir. Dry gas reservoir, where you find mainly just the gas. Mainly the gas, but accompanied by just a little bit of light hydrocarbon, a little bit of liquid. When it is reduced to atmospheric pressure and temperature. So that reservoir that is called dry gas reservoir is mainly the gas, but very little liquid hydrocarbon. The second reservoir is called condensate reservoir. Condensate reservoir is where you have gas accompanied by a large amount of liquid hydrocarbon. In the first one, it's mainly gas, very trace liquid hydrocarbon is found in dry gas reservoir. In condensate reservoir, you have a lot of liquid hydrocarbon. You still have the gas. The third one is oil reservoir, where you have mainly the hydrocarbon, the liquid hydrocarbon, and you just find the oil just like a little cap, like a bubble on the surface of liquid, where you can pinch it and it comes out. So that is how that one looks like, the oil reservoir. Okay. The gaseous hydrocarbon components are only methane and ethane. Only methane and ethane, with varying minor amounts of heavier paraffins. Olefins normally are not found in natural gas. They're not found in natural gas because they're very, very reactive and unstable. So you cannot find olefins present in natural gas. So when natural gas is composed mainly of methane, it is called dry natural gas. I want to lay emphasis on this because I realized many students mix up dry natural gas with dry gas reservoir. I want to lay emphasis here. I don't want people to keep making that same mistake. Dry gas reservoir is different from dry natural gas. Dry natural gas is the natural gas that is composed mainly methane and nothing else. Mainly methane. That is dry natural gas. It's just methane. And when we have methane, ethane, propane, other ones, butane, in addition, that are there in addition to methane, we have other ones. We describe that as wet natural gas. Wet natural gas. Dry gas reservoir is a reservoir. It's not a gas. It's a reservoir. It's a place. It's a container where you have more of gas than liquid hydrocarbon. That is a reservoir, dry gas reservoir. But dry natural gas is gas. It's not a place. It's a substance. It's gas. So please don't mix it up. Other possible constituents of natural gas are nitrogen, carbon dioxide, hydrogen sulfide, and in some cases we have helium also present. Please allow me to admit more of your colleagues in. Okay. So the term liquefied natural gas, LNG, is usually used to describe that natural gas that has been liquefied for the purpose of transportation, LNG. LNG is different from liquefied petroleum gas, LPG. LPG is used to describe variable mixtures of predominantly propane and butane. So LPG can originate from natural gas processing. So you get LPG from processing natural gas. Natural gas cannot have a double bonded compound, cannot have olefins, because olefins themselves are very reactive and unstable, so they cannot stay there in the reservoir as part of natural gas. But you will find olefins in liquefied petroleum gas because it's a part of gas that is being processed and obtained from natural gas through some petrochemical processes, which you will still find out as we go on. So LPG from petrochemical or refinery sources usually contain considerable amount of C3 and carbon 3 and carbon 4 olefins, unlike natural gas that doesn't have any olefin. So petroleum refining. Petroleum is converted into marketable products by a combination of physical and chemical processes known as refining. Physical and chemical processes known as refining. And so we will look at the two different kinds of processes. And then the first one is a physical process, which is a physical process that doesn't involve altering or touching the structure of the molecules of the compound of the hydrocarbons in the petroleum and the crude oil. So it's just a physical process. So there are physical processes that can be carried out as part of the refining process of petroleum. And we also have chemical processes. Of course, you know that the chemical processes will alter the molecular structures of the hydrocarbons. So petroleum refining begins with distillation. Of course, you know that is a physical process. It's a distillation process that will separate the crude oil or petroleum into different fractions. So it separates crude oil in the atmospheric or vacuum distillation towers into groups of hydrocarbon compounds that differ based on their boiling ranges. So you have a particular fraction that will have different hydrocarbon compounds that have different boiling points within a particular range. Maybe between, say, from 10 to 20. I'm just using that as an example. You will see exact fractions that we have here. So you will see from 10 to degrees centigrade to 20 degrees centigrade, for example, there you can have up to 5 or 6 or different compounds that have different boiling points that fall within that range of 10 to 20. That's just an example I'm giving you. So that is how the atmospheric distillation is carried out to separate the different compounds in the petroleum into different boiling ranges called fractions or cuts. Second method, I told you, in refining of petroleum, you use physical processes and chemical processes. The chemical processes is what I want to look at now. We have chemical conversion processes. These ones alter the size. They also alter the molecular structure of those hydrocarbon in the petroleum. So there are several chemical conversion processes which we will look at in the course of this study. We have this here, the conversion processes. One is decomposition, that is dividing, splitting the structures. For instance, long hydrocarbon chain, divided into smaller hydrocarbon chains. In this case, you can do it by thermal or catalytic cracking, which is a pyrolysis process, breaking down the compounds to shorter ones. That is decomposition or dividing. We have another chemical process, which is called unification. Unification is another chemical process that is carried out in the process of petroleum refining. This one entails the combining of different compounds. In this case, through alkylation, you can add an alkyl group, or by polymerization, combine different monomer units. So that's another chemical process. Another one is alteration, rearranging. It's something like isomerization and catalytic forming. Isomers, the same structure, but different structural arrangement to form compound that is completely different with different property. So that's another process that is carried out during refining of petroleum. So I need to admit some of your colleagues. Please just give me 1 second. Okay. So a large proportion of crude oil is about 90% of crude oil that is drilled is used for the production of fuel. It's only about the remaining 10% that is used for the production of organic chemicals that go into petrochemical section of the plant. So 90% of what we get from crude oil is fuel of different types. Only 10% is used for production of organic chemicals. So the first operation in the refinery, in the process of refining, is fractional distillation. That's the same one I'm calling atmospheric distillation. It's the distillation of crude oil and the fractions from their primary step. These are among the most important operations in the petroleum refinery. You cannot carry out any other step. You can't carry out any process on the petroleum until you have carried out the fractional distillation. Because it's through this fractional distillation that you'll be able to get the different compounds which you're going to use for whatever you want to use it for, whether it's for fuel or it's for organic chemicals. So you must, first of all, carry out fractional distillation in a refinery. So distillation of crude oil and the fractions is the primary step. And then the various types of distillation that are carried out in refinery are crude oil distillation, that is the very first one. You can carry out also vacuum distillation. You can carry out light oil or special product distillation. It depends on what you want. But the first one that you must carry out is the fractional distillation. And along the line, you will see some other distillations that we will carry out on already distilled fractions. Crude oil distillation, like I've mentioned, is the very first essential step in any refinery that receives crude oil. And the objective is to separate the crude oil into different fractions. So you look at this scheme here, this schematic representation of fractional distillation. Here you can see the different temperature ranges that different fractions have been separated based on these ranges. So let me admit your colleagues, please. Okay, so you can see here, you see where the crude oil comes into the fraction, the crude oil comes in here and is passed into the fractionation column. It comes in here as liquid, is passed into the fractionation column. And here you see the different temperature ranges here and the different fractions that are separated out. One liquid is passed into the column, and then several products are removed from the fractionation column. So you see gasoline, the straight run gasoline I was talking of here, that is coming out at this temperature range. And the kerosene is coming out at a different range from the gasoline. The gasoline, I'm talking of petrol that we use, the fuel we use in driving our cars. So kerosene comes as a different fraction. Diesel comes at a different fraction. And then we have industrial fuel oil. And then we have lubricating oil or paraffin wax and asphalt coming down at the bottom in a more solid form than all the other ones. Of course, the gas comes out first. Gas is the one that comes out at lower temperature, as you can see here. So, explaining more of this, industrially, fractional distillation is carried out in distillation columns, also known as distillation towers. They are like many distillation steel stacks together vertically. like you have seen in that schematic representation I just showed you. So, and then fractionation columns can be batch or continuous. They can be many in series. Several of them start from one level to the other. So for distillation to take place in a distillation column, both the vapor that is rising going up and the liquid that is condensing coming down, they must together be brought into intimate contact before you do a proper separation into different fractions. So this is done. How do you achieve this? This is achieved by, sorry, let me admit your colleagues here. So how do you achieve this? This is achieved by packing in the column, packing it with inert solids, or installing plates at regular intervals throughout the column height, like what I showed you. See some plates and regular intervals. Let me go back to the picture. These are the plates at regular intervals throughout the column. So you install these plates. And so, small distillation columns are normally packed. You have those, they are packed columns. They have the large ones, big ones have plated, like I showed you. In plated columns, we need to provide for both vapor part and liquid parts at each plate. We have to provide for vapor part and liquid part at each plate. I want to go back to that scheme, that drawing, to show you. You have the vapor part here. You can see within a plate here, you have some 4 openings here. That is the vapor part, where the vapor will go up. And then it will condense back. And you have the other liquid place coming out by the side of the wall of the column, where the liquid will flow out. The liquid will condense, it will meet up with the vapor that is going up, and then it comes to the side and flows out. So that's the explanation I'm trying to give you here. And so, what I just said, that in a plated column, we need to provide for both vapor part and liquid part at each plate, as I just shown you. The plates are perforated and the vapor passes through the perforations. Like I showed you 4 perforations from one plate. And the liquid flows through pipes known as downcomers next to the column wall, what I also just showed you. Downcomers, these are the downcomers next to the wall of the column, where the different fractions will come out. Okay. Now, products of crude oil distillation. These are the products. As you saw in that column, gases come out first. Gases consisting of methane, ethane, propane, and the butanes. These are used mostly as refinery fuel. Mixture of propane and butane called liquid petroleum gas is used as domestic fuel. So we have straight run gasoline. The gasoline you saw there that I showed you that came out first before kerosene, before diesel. The gasoline comes out between 30 and 90 degrees centigrade. That straight run gasoline is the one that is used to blend and use as the motor spirit. That is the petrol that we use. Straight run gasoline, as I explained to you before, is that fraction of gasoline that is obtained during atmospheric or fractional distillation. Then we have also straight-run benzene from the boiling point. Sorry, that BO is not BO, it's a typographic, it's BP. Boiling point from 90 to 145 degrees centigrade. It could have been used as fuel, but it's not possible because the octane number is too low for use in motor gasoline. So it doesn't have direct use. It needs to be worked on by chemical process of conversion, which we will see either by alteration or by any of those processes. Now we have also naphtha. It's also between 145 to 185 degrees centigrade. That's where it comes out. It also have the same issue with the straight-run benzene. Then kerosene. Kerosene is used as domestic fuel. We all know kerosene. It is used as jet and tractor fuel as well. We have light gas oil coming out between 240 degrees and 320 degrees centigrade. It is used as diesel and central heating fuel. So heavy gas oil also comes out at 320 to 350 degrees centigrade, just like it has some properties like that of the uses like that of the light oil. Then we have atmospheric residue. So everything above 350 degrees centigrade, those ones are within that fraction of atmospheric residue, which is used as fuel for power stations, fuel for ships, and fuel for large heating installations. One of the key products of refining is motor spirit or gasoline. That is our fuel or petrol. And the material in the gasoline boiling range is normally divided into 2 or more fractions. One of these fractions, only the low boiling material, straight-run gasoline, can be used directly in motor gasoline. The low fraction, only that straight-run gasoline can be used as fuel. And then for blending with high octane number materials. So I will, in this particular lecture of today, we'll also see more about that octane number issue. So high boiling components like benzene and naphtha, they have very low octane number, about 40, and so they cannot be used directly in motor spirits. Like I said, you will know more about octane number, what this 40 stands for today. So just give me a moment. Okay. So this particular fraction that cannot be used directly as motor fuel, as a motor or as gasoline or as a fuel that has octane number of 40 can be converted into material of higher octane number so that it could be useful for fuel. So, and how is the converting carried out is by catalytic reforming. And there are other chemical processes that are also employed to enhance the quality and quantity of motor gasoline in a refinery. Other processes that can also be used to enhance the quality and quantity are catalytic cracking, catalytic alkylation, catalytic isomerization, and hydrocracking. So if you remember the different chemical processes I listed, these are those processes. So you use it to transform the structure of the compounds in the straight run gasoline, or in the gasoline that is not in the fraction that could be used as petrol, that is not possible to use because of the low octane number. So, and then they have to be treated by chemical processes to increase the octane number and then enhance the quality of the fuel. So in a refinery, which operates catalytic reforming and catalytic cracking processes, motor gasoline is made by blending straight run gasoline. Remember one of those fractions that I mentioned, straight run gasoline? It is useful as fuel, but because of low octane number, to increase the octane number, the straight run gasoline is blended with catalytic reformate. Catalytic reformate is a product of catalytic reforming. It's a process that you also come to learn. Is still in this course. And also blending it with catalytic reformate and catalytic cracker gasoline, together with small amount of some lead additives. This is, I believe you have an idea, or you've heard about leaded fuel. This is the reason why we have leaded fuel. Lead helps to boost the octane number and bring it high. And so that was the reason for having leaded fuel, which is discouraged now. So now let's talk about octane number and the development of cracking and reforming processes. Why develop cracking and reforming processes? And then what is octane number? Development of the cracking and reforming processes were as a result of low quality fuel and low octane number fuel. So developing these processes help to boost octane number and also enhance the quality of fuel that we use. So about 10% of the products of the distillation of crude oil is a fraction known as straight run gasoline. It serves as a satisfactory fuel during the early days of internal combustion engine of the car. In the early days, straight run gasoline could be used directly as it is brought from the refinery. That fraction can be used directly in the vehicles. But as time went on, automobile engine was developed in such a way that it's made more powerful by increasing the compression ratio, the gas compression ratio. So now modern cars run at compression ratios of 9:1, which means the compression ratio, of gasoline and ordinary air. Ratio of 9 gasoline to ratio of 1 of air. So that is gasoline air mixture, 9:1 in the cylinder. So this is compressed by a factor of 9 before it is ignited. This is how the modern cars run now. So straight run gasoline that was used before in the cars in the olden days, they burn unevenly in high compression engines. Of course, our current vehicles use automobile engines that are having high compression ratio, increased compression. So with that, straight run gasoline, if it is used, it burns unevenly in such engine So burning unevenly makes it to produce shock waves in that engine and causes engine to knock. So the car engine can knock if you use straight run gasoline directly. And the reason is because it burns unevenly and produces shock to the engine because of the high compression in the current modern automobile engine. So why am I going here? Trying to tell you why develop cracking and reforming processes. Trying to also explain to you what ISO I'm trying to explain to you also octane number. So to avoid knocking of engine, that is why these cracking processes and then reforming processes were formed. So as to produce other compounds that are more stable when they are burning. And then you can mix it with the octane, with the straight run gasoline and make it to be more stable when burning so as to avoid knocking of your engine. Okay, so now the challenge for petroleum industry is what warranted the development of cracking and reforming. The challenges are that of um, low octane number and also low yield of gasoline from each barrel of crude oil. So to increase the yield, there are some processes that are carried out, which are the cracking and reforming part of those processes, and also to boost octane number, these processes also come into play. And there are some factors that are of great importance that, help in knowing how to or what to do to boost octane number. These ones I list here. Number one, that branched alkanes and cycloalkanes burn more evenly than straight chain alkanes. I mentioned to you that the straight run alkane burns unevenly and produces shock. But branched alkanes and cycloalkanes, they burn more evenly than straight chain alkanes. So these processes will help us to produce from straight chain alkane, will help us to produce branched alkanes and cycloalkanes and cause them to burn more evenly without giving shocks. The number two is that short chain alkanes burn more evenly than long ones. For instance, the carbon-4 alkanes, they burn more evenly than the higher ones, carbon-7. So these processes that are developed are to break down and crack the long chain hydrocarbons to shorter ones to enhance the even burning. Also, alkenes, number three, alkenes burn more evenly than alkanes. So to convert the alkanes to alkenes, that is what this process, the essence of this chemical process, to convert the alkanes to alkenes. And then also number four, aromatic hydrocarbons burn more evenly than cycloalkanes. So it looks like the aromatic is really very good. So it means this alteration and so on chemical processes have to be carried out on the straight run gasoline so as to have them in aromatic form. So if you convert the alkanes to cycloalkanes, yes, it's good, but it is better if you further go on and convert the cycloalkanes to aromatic hydrocarbons. So it gives a much, much more stable burning. So the most commonly used measure of gasoline's ability to burn without knocking is what is called octane number. The most commonly used measure to assess the ability of gasoline to burn without knocking is what is called octane number. So what does octane number do? It compares a gasoline's tendency to knock an engine of a car, compares the tendency to knock against the tendency to knock of a blend of two different hydrocarbons, heptane and 2,2,4-trimethylpentane, otherwise called isooctane. So what this means is that you will use your gasoline as it is, and then also keep your gasoline aside, and then keep the blend of these other two, the heptane and isooctane, aside. And then carry out a step. So we'll see some steps that can be carried out, some procedure. Carry out a procedure of trying to knock, the tendency to knock, and compare that of that particular gasoline, the tendency to knock of that particular gasoline, to the tendency to knock of the other blend of the two, heptane and isooctane. So if the gasoline knocks, so at the time that the blend of the two knock, at that point, then you can say that that gasoline has a particular number. So I think I can explain this better. So heptane produces a great deal of knocking, while isooctane is much, much resistant to knocking. So when you blend heptane that knocks so much, you blend it with isooctane that doesn't knock. You now use that to check the knocking of your gasoline. So gasoline that matches the blend of, now you have you have to be changing the blend. You have to changing the composition of your heptane and isooctane. Maybe you add a little bit of isooctane, and then you add more of heptane, and then you now carry your gasoline and try and see where it will knock. So if you have a blend of, if you have an octane number of 87, that is 87% of isooctane and 13 of heptane. This one gives an octane number of 87. So the blend of 87 and 13, 87 of isooctane and 13 of heptane gives you an octane number of 87. So if you try to check when your gasoline will knock, and it knocks much, much, much different from this, then you can keep trying the different ratios of your mixture of isooctane and the heptane. So, and then you'll be able to get the particular mixture at which your gasoline knocks at that same type of mixture, that same mixture. So then you will call your octane number for that, your gasoline, what it is based on the blend of your isooctane and the heptane. I believe that is clear enough. So how do you measure octane number? You can use different types of methods to report your octane number. One is the one that you measure at a high speed and high temperature. At a high speed and high temperature, I mean speed of your car and high temperature, then that one is called motor octane number. So while measurements under relatively mild engine condition is known as research octane number, the second one. And the third one, the third measurement is called road index octane number. And it's an average of the two. It's average of motor octane number. If you test your gasoline and you have a particular octane number, and blending that one with what you get from research octane number gives what is called road index octane number. So road index octane numbers for a few pure hydrocarbons are given below. I have some road index octane numbers to show you here. So like I've told you, heptane burns very so much. And so the road index octane number for heptane is 0. We have for 2-methyl heptane is 23. Then hexane is 25 and so on. You can see isooctane is 100. And benzene and toluene 101, 112. So the blend of the 0 and 100, so you have that one that burns too much, and the one that is no octane number, and the one that has. So now we are comparing the straight run gasoline or your gasoline with a range of 100. So it's like 100%. So if you have your octane number, that is a comparison of your gasoline and that of a mixture of heptane and isooctane. If you have your octane number for your gasoline up to 97, it's a very good one. So the higher the octane number, the lower the tendency of your car engine to knock when it is using that fuel of high octane number. So in 1922, a number of compounds had been discovered that could increase octane number of gasoline. Adding a little bit, like 6 mils of tetraethyl lead to a gallon of gasoline, for example, can increase octane number by 15 to 20 units. So this discovery gave rise to the first ethyl gasoline and enabled the petroleum industry to produce aviation gasoline with octane number greater than 100. Another way to increase octane number is thermal reforming. Thermal reforming. At high temperatures between 500 to 600 degrees centigrade, a high pressure and at high temperature of 50 to 600 degrees centigrade, and also at a pressure of 25 to 50 atmosphere. At those conditions, straight-run alkenes will isomerize to form branched alkenes and cycloalkenes, thereby increasing the octane number of the gasoline. Remember, I told you that alkenes burn less evenly. So branch alkenes, cycloalkenes, they burn more evenly. So you can carry out thermal reforming to isomerize your straight-run alkane into these other ones, and that will boost the octane number of your gasoline. Running this reaction in the presence of hydrogen and a catalyst will really enhance will produce even higher octane number. What I mean is that if you carry out thermal reforming in the presence of hydrogen and also add catalysts such as a mixture of silica and alumina, you will have very good results. It will result in even higher octane numbers. So the yield of gasoline is increased by cracking. The long hydrocarbon chains are cracked into smaller pieces at high temperature and high pressure, as stated here. So that cracking will increase the yield of your gasoline. Remember, I said two key things that were necessary. You know, the refiners are looking for high yield of gasoline. They're also looking for gasoline that have high octane number. So cracking the long chain hydrocarbons, we break them down to smaller ones, and then this will increase the high yield of gasoline. And also the other process of cracking, catalytic reforming, and so on, will also help to boost the octane number and make your gasoline more useful and less susceptible to knocking. So a saturated carbon-12 hydrocarbon in kerosene, for example, might break into 2 carbon-6 fractions. So in that case, that is also helping to boost, to increase, of course, remember I said short chain hydrocarbons, they burn more evenly than long chain. So when you break these, they will help to boost octane number, burn more evenly, and they also help to increase the yield. Because the total number of carbon and hydrogen atoms remain constant. So the product of this reaction, so when you're carrying out this cracking, definitely you will have to end up with some olefins also with double bonds, because you won't remove the carbon remains the same. You could lose the hydrogen to another compound because of the reduction in hydrogen atom.
Sorry, ma, it's past 5 p.m. We need to attend another class, ma'am.
Okay, all right. So that's the end of the lecture, and we're just at the end of the lecture now. Okay, so I will stop sharing, and you're very free to go for your lecture. I've concluded. All right. If you don't have any question, anyone that has question can ask. Otherwise, I'll bring this lecture to a close today. I will send the link to you also, so you can go through it.
Thank you, ma'am.
Spare time. All right.